Good morning. It's morning in America. In fact, my first magic trick of the evening is getting here, because I flew all the way from Washington, D.C. to Iceland, to the UK, to Serbia, to finally end up in Slovenia. And I'm really excited to be here tonight. I promise not to fall asleep until after my keynote and after I've had a chance to talk with as many of you as I can. Tonight, my talk is about magic tricks with functional effects. Functional effects are often thought of as a better future. And it is true, functional effect does give you something that is a better future. But it's way more than that, and actually, some of the properties of functional effect systems give you the ability to do things that are not possible to do with future. In fact, they go way beyond anything you can do in the world of side effectful programming. Some would even call these abilities magical. Too much? Well, let's wait and find out. Let you be the judge of that tonight. I'm going to start off by talking about what functional effects are. And my goal is for every one of you to leave here today with a deeper understanding of what a functional effect is and how it enables functional programmers to solve programming in the large. Then I'll talk about Zeo a bit, an introduction to the functional effect system that I work on. But I'm actually going to give you a different introduction to Zeo than you've ever seen before. If you've ever seen anything else I've done, I'm going to give you a toy example, a toy implementation of Zeo so small it actually fits on a single slide. And that's going to help you understand what functional effects are in I hope, a fashion that's way deeper than most of the people out there who are using these systems actually understand them. And in part 3, I'm going to give you a tour of some really cool, I'm going to call them magic tricks that you can do with functional effects. And the goal here is not necessarily to teach you a bunch of practical stuff, even though a lot of the stuff that I cover will be useful in some way you'll be able to see. But rather it's to leave you with a sense of, oh, wow, when your program is converted into a value, and you can now store that value in data structures, and you can pass it to functions, and you can return it from functions, and you can build combinators and custom control flow structures on your own programs, that is incredibly powerful and opens up a whole world of programming. It's a taste of what programming with functional effect systems really is. And finally, if I've intrigued you enough at that point, I will give you a few tips on how you can learn more if you want to become your own magician with functional effects. So let's get started with functional effects. Functional effects are us functional programmers' version of a side effect. What is a side effect? Well, a side effect is anything that does something with the outside world. It's an interaction of some type with the outside world. If in any function, that function interacts with the outside world in an observable way, then we say that that function is performing a side effect. Now, side effects are great because they let us ship code that actually does stuff in the real world, right? That's a good thing. But side effects are also not so great in the sense that they decrease our ability to reason about our programs looking just at the types. And not only that, but they aren't very composable. Side effects don't compose. And they're really, really hard to test. So functional programmers have come along and invented something called a functional effect that lets us interact with the outside world, but with improved type safety, improved composability, and improved testability. And that thing is called a functional effect. The core idea in a functional effect is that instead of doing something right now, we're going to describe it by building an immutable data structure. And then later, at the end of the world, at the edge of our program, in our main function, we'll go ahead and translate that description of side effects into the side effects that it describes. So functional effects are descriptions, immutable values, that describe side effecting operations, interactions with the outside world. Now let's say we want to build a functional effect to describe the operation of printing a line of text to the console. Then one way we could do that is we could say, well, every console effect is going to be either a print line operation, or it's going to be a sequence operation which has a first and a second operation. And we could implement this in Scala in very straightforward fashion by using a sealed trait. In the sealed trait, we introduce an operation called plus that, given this console object and this one, can combine them together into a single one using the sequence operator defined below. The print instruction stores the line of text to be printed, and the sequence instruction stores both the first component and the second component of that sequence of two console operations. Given this simple data structure, we can actually describe console programs. They're not very fancy. In fact, all they can do is print stuff out in sequence. This program here prints hello, a new line, and followed by world. We can describe the entire class of programs that do nothing but printing a bunch of things in sequence using this simple, purely functional, immutable data structure. Of course, if we want to do console input-output programs, this guy isn't going to cut it, is it? Because it doesn't allow us to read anything from the console. We can only write things, and that isn't very useful. If we want to take the next step, if we want to describe interactive console programs, then we've actually got to modify the structure considerably. But before we get to that, let's take a look at how we would implement a run function for this console effect. This run function would be responsible for taking that description of console effect and translating it into the side effects that it describes. In this case, we accept the console as input, and we match against both different terms in that sealed trait. Every console is either a print of a line, which we translate into a literal print line, or it's a sequence of a first and a second, in which case we translate that into running the first, followed by running the second. And here we have what would be called an interpreter using FP terminology. This is an interpreter that translates a description of console effects into the side effects that it describes. Now, this interpreter, calling this interpreter, is not a very functional thing to do, because this is going to be non-deterministic. It's going to interact with the real world. But in the ideal case, if you're building your own FP app, you can push almost your entire program into the world of pure FP, and you're left with a tiny little snippet that calls some interpreter that translates that immutable data structure into the operations that it describes. So if we want to add interactivity to this data structure, then we actually have to extend it in quite a bit. We actually only need to add one more term, but the structure of this is much more complicated. The first change we have to make is we have to introduce a type parameter A here, so that console becomes not just a monomorphic data type, but a polymorphic data type. And the interpretation of this A parameter is the value with which a console effect succeeds. So console of A here thank you. That's better. So console of A here represents a console effect that, if it succeeds, will produce a value of type A. If you want to think of effects as being programs, basically programming languages that we've embedded into Scala, then you can think of this A as being the return value of our program. So every console of A is either going to be a return statement. This is a pure program that does nothing other than return a value of type A. Or it's going to be an instruction that prints a line of text to the console, and it does something else after that. Or it will be a read instruction that, when fed a line of input from the console, can produce the rest of the program. Implementing this in Scala is very straightforward. We just use sealed traits again. And we have three different terms in this sealed trait: the return, which stores a value of type A; the print, which stores that line of text together with the rest of the program; and then the read statement, which stores a function that, given a line of input, will produce the rest of the program. Now we can describe the entire class of interactive console programs. There's no program that you can describe, no matter how complicated, as you can't describe using this very, very simple data type. Programs look like this. So this particular program, it describes an effect that succeeds with a string. The first instruction in this program is print line. It prints out this line of text to the console. And then the rest of the program is everything inside these parentheses. The next instruction in the program is a read. instruction. And the read instruction is defined by this function here that takes the line of input read from the console and then produces the rest of the program. And in this case, the rest of the program is yet another print line instruction that prints out hello name and then continues with the rest of the program. And the rest of the program in this case merely returns the name that was read from console input. So here we have an interactive program that reads something from the console and reflects it back out to the user. This program is a pure data structure. It's a pure value. It doesn't actually do anything. If you evaluate this in the console, you'll just get back a data structure. It's like Scala's list. If you want this to actually execute, then you need an interpreter, and you have to write that interpreter. The run function just matches against all three cases, and it translates every description of a side effect into the effect that it describes. The return translates as a pure return. It actually doesn't do any side effects. The print translates as printing that line and then running the rest of the program, the K there. And then the read actually reads that line of input from the console and feeds it to K, that's that function stored in the read constructor, which then produces the rest of the program that is then run recursively. So that's it. That's what functional effects are. They're immutable data structures that describe side effects. And at the end of the world, at the edge of your program, whatever that means for you, you have to run them. You have to interpret those immutable data structures into the side effects that they describe. Now let's take a look at the functional effects system Zeo. Zeo is the open source library I work on. It's positioned as a better future or as a library to help you do async, concurrent, and very soon distributed programming in Scala. The Zeo effect type, though, unlike console and unlike future, actually has three type parameters. Now, these three type parameters are R, E, and A. Zeo REA is an immutable value. It's a functional effect that describes some sort of side effect. And the meaning of these three type parameters is as follows. First off, we have the R type parameter. The R type parameter is referred to as the environment of the effect. This is the thing that the effect needs in order to be run. So different types of effects can have different dependencies. Some effects could depend on a database connection. Other effects could depend on a web service, a particular web service. Others could depend on system clock time. Still others could depend on some sort of database repository, like a user repository or so forth. And others might depend on application context or configuration information or session information or Spark session or whatever you want. That R-type parameter is there to allow you to express the idea that your effect cannot be run in isolation. It needs a context. It needs something from its environment in order to be run. The E-type parameter represents the type with which the effect may fail. So it's an error type. Future has one of these, only it's fixed to be throwable. So the error type, the error channel inside Future, you're not allowed to change it. It's like the error type in try. Try can fail for some throwable reason, but you can't change that error type. Either, on the other hand, is a data type in Scala with a polymorphic error channel, which means you can actually change that error type to be your own custom error type or eliminate it entirely. And then finally, that A-type parameter is the one that you know from Future. It's the type with which the effect may succeed. So every Zeo of REA represents an effect that needs an R and either fails with an E or succeeds with an A or possibly runs forever. Now, I'm going to introduce to you a very simplified model of Zeo. This isn't actually how Zeo is implemented, not at all, not even remotely close. However, this is a very good mental model. If you get this in your head, you'll have a very, very deep understanding of how to use Zeo. The mental model is as follows. Every Zeo of REA can be thought of as a function. That is, this is a case class here. This case class stores a single function here called run. And this function takes an R and is going to give you back either an E or an A. The interpretation.
Do not do the mouse over because we can't see the whole slide. The rest of it goes div
This? Is this better? Oh, yeah, wow. Oh, okay, sorry. It doesn't look that way on my screen. All right, so this R is what the effect needs in order for you to run it. You have to give the effect an R in order for you to run it. And this either EA represents what you can get out of the effect after you run it. Every effect, if it returns at all, is either going to fail with an E or it's going to succeed with an A. Now with this simple definition of an effect type, we can now talk about constructors, so ways to build values of this type. And one of the simplest possible constructors would be a succeed constructor that takes the value of type A and returns an effect that succeeds with the value of that type. This type here says this effect doesn't need anything. It says it doesn't need anything because its R-type parameter is any, which means to run it, you can give it any value you want. You can run this effect with a unit value or a string value or any type of value you want. So this is an effect that doesn't require anything. You would not use nothing as this type parameter here to indicate an effect that doesn't need anything, because that would be an effect that actually can't be run. You can't produce the value of type nothing. So if you use nothing in this type parameter slot, you would make an effect that no one could ever run. The nothing in this error type parameter says that this effect can't fail. You know that by looking at its type. There are no values of type nothing, so there's no way anyone could have constructed a Zeo effect that fails with a value of type nothing. There are no values of type nothing. And finally, this effect succeeds with a value of type A, and it does so by taking this A value in, and then in this function from R to either EA, it merely wraps that A inside the right-hand side, which represents success. In a similar fashion, you can define a fail constructor that, given a value of type E, returns an effect that fails with that E. And note, this effect doesn't require anything, and it cannot succeed. And we know that by looking at the type. This is an effect that cannot succeed. This constructor gives us an effect that takes whatever is in the environment, this R parameter, and returns it as the success value of the effect. This gives you access to the environment. And it does that by, inside this function that takes the environment, it just takes the environment and wraps it up in that right constructor to succeed with that environmental type. And then this constructor is the single most important constructor in the whole deck. If you understand this, you'll have a very deep understanding of functional effect systems. What effect does is it takes a side effecting, potentially exception throwing piece of code. This is a by name parameter here. And it tells Scala not to evaluate whatever sort of expression you feed it in between these parentheses. So what you're feeding it is in fact a side effect. It's something that's going to interact with the external world. It's going to talk to databases, it's going to do logging, it's going to make web API calls and so forth, and it may even throw exceptions. And then what's going to happen is this side effect is going to be converted into a pure immutable value that does nothing other than describe. And it's going to be converted to that value by using the Zeo constructor here and trying to run this action, feeding it into the right constructor here, but catching any throwables and feeding them into the left constructor here of the either. So what happens when effect is called with something like printline or whatever it might be is that it merely bundles up that bit of side effecting code into a data structure, storing it there. And then later, at the end of the world, when things are run, it's going to try catch that, and it's going to translate any exceptions inside that code block into failures in the error channel. And then finally, for sake of completeness, notice that because Scala has no means to prevent us from throwing exceptions anywhere, it makes sense to define a constructor that does nothing other than blow up. This is called die in Zeo. and it throws an exception. You probably guess what it does. It throws an exception basically inside that run function that we looked at, which is one of the possibilities. A function from R to either EA doesn't have to return an E or an A in the either. You could also throw. And that's what this die function does. Once you have a data type like that and ways to build values of that type, you can start talking about operations on effects. Operations on effects are how you build bigger effects from smaller effects. They are how you build bigger programs from smaller programs. In a similar fashion, how we build bigger side effects from smaller side effects is we list them on different lines. It's actually the only operation we have on a side effect is we can put one side effect on one line and then another on another line, hence composing two side effects to form one side effect. Functional effects are more powerful. We have more means of composing two functional effects than just that sequence operation. So this this operation here is called map, and it's the one you know and love from Scala's future and so forth. What it allows you to do is to change that A value, the success value, into a different value of type B. The flat map operation, which is also more or less the same as future's flat map, allows you to flat map over the success value. And you can think of this function that you pass to flat map as being a success handler. It's a success handler. Because with the success of the first effect, that A value, you're allowed to produce the rest of the effect, which will be some other effect that produces a B. And flat map is in some fashion combining an effect together with its continuation effect to produce an effect that succeeds with the B value. Flat map is how you do two things in sequence, where the second thing depends on the value produced by the first thing. This is the power of statement composition in procedural programming. Because in statement programming, subsequent statements can refer to values produced by preceding statements. And in a similar way, when you have a bunch of flat maps, things more deeply nested inside can refer to values that were produced by prior effects. Flat map is the essence of imperative programming. And then we have this interesting operation called provide that's able to give an effect what it needs to eliminate its requirement. So when you give an effect in R, you now get a new effect out of there that doesn't require anything. And it works just by giving the effect its R value. This either operation takes the E inside the error channel and pushes it over into the success channel by wrapping the error and the success in an either. It allows you to move that error information out of the error channel into value space, the success channel, where you can operate it with operations like map and flat map. This is the key to error recovery, error handling. The zip operation takes two effects and zips them together to get back a tuple that produces whatever the first effect produced and whatever the second effect produced in that order. And once you have zip, it becomes very natural to define a zip left operator that zips two things together and maps to return the thing on the left-hand side. You can think of it as doing the first and then doing the second, but returning the thing on the first side. And then we have a zip right operator that you can think of as doing the first and then doing the second, but returning the thing on the second. This is all that's necessary to describe very rich programs. In this example, I've implemented a purely functional version of print line and read line. And how we do the print line is, we just call the ordinary print line, but we do so inside the effect constructor. So we get back here a pure value that describes the operation of printing a line of text to the console, but doesn't actually do anything. And then in getStirLine, which, note, actually becomes a value here. This is not a method. This is an ordinary value. It's a static value, never changes. This getStirLine is an effect constructed by wrapping readLine, Scala's readLine, inside of this lazy by name constructor. So what we've done is, again, we've translated this side effect into a functional effect by storing a description of what that side effect does. And with these two operators, together with flatmap and map, we can define our first interactive program. Here I define it using a for comprehension, which is nothing more than sugar for a bunch of flat maps followed by a final map. So in this program, we print out, hello, what is your name? Then we get the name from the user, and we print out good to meet you name, and then finally we return that name. This is the equivalent of that program we wrote earlier on with console. This is just a toy data type. It's not designed for production programming. Please don't try to use it inside your application. The RealZo data type is implemented in a different way, and it handles not just success and failure values like you saw here, synchronous effects like you saw, but also async effects. So it allows you to delete callbacks. It handles concurrent effects, cancellation effects, so you can cancel computations that are in progress, dependency effects, parallel effects, and resource effects. So even though Zeo does let you do everything we've talked about today, it's much more than that. It's a fabric on which to build modern applications that are async and concurrent and have to be robust, testable, and ideally type safe. All right, that's all the time we have for a background on Zeo. Now we're going to dive into magic tricks. And we're going to start off simple, relatively simple, and we're going to throw in some stuff for you advanced functional programmers who have already been doing this for a while. Let's talk about fallback operations. So Zeo has a really interesting operator called or else. And or else lets you compose one effect with another effect in the following fashion. The resulting effect will try the thing on the left-hand side. And if that fails for any reason, it will fall back to the thing on the right-hand side. And one of the really cool things about Zeo is that because it has a typed error channel, the Scala compiler can actually track whether or not effects fail as you move them through different operators. In this case, we have a getFromCache function that can return an effect that could fail with a throwable. Task is a type alias for an effect that may fail with any throwable. Then we have a getFromDatabase function that could also fail with a throwable. But then finally, we have a getFromConfig operation that can't fail. And we chain them all together in getFromSomewhere by using or else. So we're composing three effects in here. And the Scala compiler looks at this chain of or else, and it sees that the fallback of the fallback operation cannot fail, so it knows that the composition of all these three effects cannot fail. So we have static compile time proof that we've handled all our errors in getFromSomewhere. This can be used to help you do principled error management. If you want to guarantee that some bit of code can't fail, or that it can only fail in one of a preset number of ways, you can add that type signature to that method in advance and say, this is what I want to get out of this. And then, as you start editing your code, the Scala compiler will helpfully tell you whenever you stray off the happy path and you start producing the wrong type of errors or failing to catch errors that you should have caught, and so forth. One of the really cool things that becomes possible when you take side effects and you convert them into values is that you can define effect combinators. These are custom control flow structures. Effects are ordinary values, and you can define functions that take effects and return effects. And one such effect that's almost sort of mind-bogglingly simple to define is forever. The forever combinator takes an effect and gives you back one that just goes on forever, repeating the effect of the original one again and again and again. It's very simple to define this. All you do is you do this effect first. Using the zip right operator, we do this effect first, and then we follow that by forever on Zeo. So this is a recursive call to forever. So if you expand this out in your mind, you're going to get Zeo, zip right, for Zeo, zip right, Zeo, and so on, and so on, and so on, forever. This just repeats that effect again and again and again. And you can see by looking at the type of this combinator that it doesn't succeed with any value. It can still fail with a value of type E, but it can no longer succeed. This just goes on forever. So not only have we defined our own custom control flow structure here, we've done so in a very simple way, and we've been able to use the Scala compiler to help us reason about the termination properties of things that you get out of this forever combinator. They don't terminate. And we might use this as follows. We might have a cache we want to refresh forever. So we just fetch the data, we store it in the cache, and we sleep for 60 minutes, and we put it in a loop to get back an effect that does all of that in an endless loop. The dual of forever is eventually. And to make eventually, we create this function here that takes an effect and returns an effect that can't fail. And it does that by basically trying the Zeo effect, or else it goes on to eventually Zeo. And if you expand this in your mind, then you get Zeo or else, Zeo or else, Zeo or else, Zeo, etc., an infinite chain. So this effect here, it can't fail. It can succeed, or of course it could run forever. If this original effect just keeps on failing, the resulting effect here will run forever. Now let's say that's cool, but what if we took this up a notch? Well, in order for us to have maximum power in our programs, we would need a value that's capable of describing according to what schedule to do some sort of retry. This is called schedulingzeo. And in this little code snippet, I define a schedule that has the following properties. It starts off with exponential retry spacing, starting from 10 milliseconds and doubling every time thereafter. So it's going to start out at 10 milliseconds, and then after 10 milliseconds, it'll increase the duration between retries to 20. And then after that, it'll increase the duration of retries to 40, and then 80, then 160, and so forth. However, it uses the union operator, schedule union, to combine that with another schedule that is spaced 10 seconds apart. And what union does is it will continue the schedule as long as both of these schedules want to continue, and these schedules will continue forever. But it will also choose the minimum of the durations produced by these two schedules. So this one wants to wait for 10 milliseconds to start with, this one wants to wait for 10 seconds to start with, so this minimum duration will be the one on the left-hand side. And it will continue until the spacing between these exponential fallouts exceeds 10 seconds, and then it will switch over to this spacing, which is 10 seconds. So we'll end up capping our spacing to 10 seconds. And that's not enough because we want to cap the total number of retries that we do. So we do schedule intersection over here, which will only continue as long as both of these schedules want to continue. So it's only going to continue for as long as this one and this one want to continue. And the recurs 100 will only want to continue for at most 100 times. So we end up composing all these schedules to get another schedule that will start off with exponential fallback behavior until it reaches 10 seconds between retries, and it will continue for up to 100 retries. And that's not enough. We add some jitter just for good measure, so random jitter, and then we do a zip write to collect all the errors and log them to the console. And any schedule you can imagine, any retry policy or sort of repetition schedule you can imagine can be defined just as simply in just using a few small number of operators in a type-safe fashion that's 100% deterministically testable from a unit test. And here I use this schedule to define an HTTP GET operation that merely calls ordinary GET but retries it with this specified retry policy. Zeo has built-in support for parallelism. In fact, this parallelism using operators like for each par is not actually intrinsic to Zeo. You could write for each par yourself using something even lower level in Zeo, which is the fiber-based concurrency model that allows you to fork effects, run them in different fibers, and then join them later. This for each par allows you to execute in parallel all iterations of a loop. So we can use this to define a load tester in one line of code. All we have to do is do a for each par from 0 to n. So now we are executing, we're basically iterating over all numbers from 0 to n in parallel. And then with every one of these numbers, which we ignore, we're going to do an HTTP GET of the specified URL. Then we're going to call either on that to allow us to move that information from the error channel into the success channel as an either. And then we're going to map over that either and get the left projection and convert that to an option. So what we get out of this entire loop is basically a list of options. We get back all the things from every iteration in the loop. And with that list of options, we collect them and look for the cases where we got an error, and we extract those errors out. So here we get an n-way concurrent load tester that collects all errors and gives them back to you in a list. And this is just one of many things that we could do, of course. We could decide to retry failed transactions. We could time out individual transactions or the whole. And all these are just more operators on the basic effects. What this gives you is a level of power and expressivity that you just can't achieve using other techniques. And it comes directly down to the fact that effects are ordinary values you can define operators on that take and return effects as values. One of the really cool things and really mind-blowing things about Zeo is that you can actually define an operator called flip that takes the error and the value channels and flips them. It moves the error over to the success and the success over to the error. And then, of course, you can flip back and end up with whatever you started with. This allows you to do some very interesting things. For example, let's say we want to map over the error channel. We could define an operation called mapair that flips the effect, allows you to map over the success channel, and then flips it back again. Mapair is how you change the error type from one error into a different error type. Not just mapair, though. It turns out we can take every single operation in Zeo defined on the success channel, and we can flip it, execute that operation, and flip it back, and we get back something really interesting. What you get back depends on what operator you flip, but I'll give you an example. You can actually define eventually, which is going to try something again and again and again until it succeeds, in terms of forever, which tries something again and again and again until it fails. And you do that just by flipping the effect, calling forever, and then flipping it again. And this is just one thing. You could go into Zeo now, you could grab out one of the operations on the success channel, and you could invent a new operation by flipping it, doing the operation and flipping it back. And you might even discover something that's actually pretty interesting and useful that no one ever thought of before. In fact, this one was discovered in a similar fashion. What's the dual operation of forever? Well, it's eventually. This one uses that in a really interesting way to do a for comprehension, a sequence of chained operations over the error channel. And the interpretation of this is really interesting. So the idea here is we're going to execute a fallback plan. We're going to try this first plan, plan 1. But if we get a specific error out of this, we're going to try fallback 1. Otherwise, we're going to try fallback 2. How do we do this? Well, we need to do this chain of computations where subsequent computations depend on values, failure values, produced by preceding computations. So the operation we want here is flat map, but flat map's wrong. Flat map operates on the success channel, not the error channel, so we just flip it. We flip plan 1, and now we get access to the error of this effect. And then if that error is equal to the specified error, we're going to execute fallback 1, otherwise we'll do fallback 2. We'll flip this whole thing, so we get back the error of all of this, and then we're going to yield that error inside this block. So this is a for comprehension that is operating on the error channel of the effect. And then we flip the whole thing back because we want a task out of this. So we've all been in the situation where we've had a for comprehension, and we've had one method that returned a try, and another that returned an option, and another that returned an either, and another that returned a future. And you know, the very first time you're using for comprehensions, you probably don't even know exactly how they're desugared and what's going on here. So you put them all in the same for comprehension, and what happens? Scala gives you this really indecipherable error message. And part of it's indecipherable because of the way for comprehensions are desugared into flat maps and maps. But it's very confusing, and it takes Scala developers a long time to learn you can't mix different data types inside the same for comprehension. You always need to be flat mapping over the same thing. And this leads you down a long, scary path to monad transformers. That results in you writing a lot of code that your coworkers are going to rip out the day you leave. You don't need monad transformers when you're using Zeo. Because what you can do, Zeo has enough capabilities that you can take all these different data types, and way more besides this, and you can lift them up losslessly into the Zeo effect type. How do you do that? Well, you just call different methods on Zeo, like from try, from option. It's a water pistol. Don't get any funny ideas here. From option, from either, from future. You just lift them all up into the Zeo data type, and now you can stick them all in the same for comprehension. And this would apply, by the way, even if we were using much more complicated types. Like if we were using types that you might think you require option T of either T of, state T of future, you don't actually need a monad transformer for that type. You can lift all of that up into a flat Zeo effect. Zeo also has built-in support for cancellation. And this lets us do something really amazing, which is to find a combinator called auto shutdown that's going to take a task and give us a new task. Only the new task has a really cool capability. It has the capability such that if the JVM is shut down for any reason, it will cancel this running task, and it will safely clean up everything and wait for everything to be cleaned up and wait for everything to be shut down before the JVM actually exits. And it's amazing how few lines of codes it takes to define that. We use this runtime operation to get us access to the Zeo runtime, and then we fork the main effect into a separate fiber, which gives us a fiber. And then what we do is we call this Java method called getRuntimeAddShutdownHook to add an unsafe run of the fiber interrupt method into the shutdown hook. So now when the JVM shuts down, it's going to call the runtime's unsafe run on the fiber interrupt method. And that interrupt method is going to work its way down the entire tree of our program. Doesn't matter how deep it is or how wide it is, it's going to shut everything down. And it's going to safely clean up all allocated resources. And doing that in an ordinary application is untenable. There's no way to do that. And even thinking about the amount of work that it would take to implement that in your application is just mind-boggling. But you get stuff like this for free when you're using a functional effects system like Zeo. And then finally, we join this fiber that we forked up here to get the A out of it, and then we yield that A at the bottom of the for comprehension. And the last example we'll take a look at is an example using STM. I'm sure we're all very hungry, and we're probably going to go out to eat after this. Well, let's say we go to a restaurant. We all try to cram into the same place. Well, there's only going to be so many seats at the table. And we're all going to try to eat. So let's see if we could use Zeo STM to solve this problem in a way that's concurrent safe and actually allows everyone to eventually eat their food. How we do this, Zeo STM gives us software transactional memory. And the way to think about software transactional memory is it allows you to have database-like transactions over memory inside your application. So you can create transactions that are atomic, they're consistent, and they're isolated. And they touch multiple regions of software transactional memory, and they do updates to all of them in a consistent, atomic, isolated fashion. And not only can you do all that, but STM allows you to have preconditions. and say we're only going to commit this transaction when this condition is satisfied. And when you commit a transaction like that, what happens is if the conditions aren't satisfied, the transaction itself suspends. And then later, when the condition is satisfied, when someone updates something and it ends up being satisfied, then the transaction will resume and complete. And you don't have to worry about the mechanics of how that's implemented. You can work at a much higher declarative level, which is, I want to commit this transaction and I want these preconditions to be satisfied. To implement this, in order for all of us to eat, this is what we have to do. We have to model the problem as a T-array of Booleans, the seats as a T-array of Booleans. So this is an array with a bunch of Boolean values in it. And the Boolean values are going to be false or true, depending on whether or not the seat is taken. And then what we do is we loop over all the people, which is a list of these T-refs. Every T-ref is a transactional reference that holds the state of being either full or hungry. And then for each person inside this list of people, we eat dinner. In the eat dinner method, what it does is inside this for comprehension, it looks for a free seat by scanning over the seats and looking for one whose entry is false. And then it calls this collect method on this transaction here, which allows us to supply a partial function. Partial functions do two things. They allow you to map over a value, but also to filter it. You can map and filter at the same time. And the way this collect method is defined on an STM transaction is, it will, if this condition is not satisfied, if your partial function is not defined for some input, it will suspend the transaction until conditions are satisfied. So in this case, we're saying we want to find some place to sit. We don't care where, we don't care when, we just need a place to sit. And then what happens is, if we try to sit too many people at the table, the transaction will suspend until there's enough room. And when there is enough room, the transaction will resume. This line of code will actually succeed in collecting an index out of here, and the rest of the transaction will continue. If you're interested more in STM, I believe, Lek, you wrote the, didn't you write some of that code? TRA. TRA, yes. So we've got the author of TRA here. And then Wiem and I worked on the STM implementation, and there's a different talk on that. All right, so functional effect systems, they offer a lot of power. They offer a lot of power because they turn side effects into ordinary values. And when your programs become described by values, you can now define your own custom control structures and combinators. And that's amazingly powerful. These things you can't do. None of the things that we talked about tonight you could do with Future. None of them. They all require the power of pure functional programming, the power of laziness, the power of being able to describe something without actually doing it. And the more you wrap your mind around the fact that functional effects don't do, they just describe, the easier it is to start programming in this fashion. And eventually, you will reach a point where you become insanely productive using a functional effects system. Yes, I'm not going to lie to you. You have to learn how to program using flat maps and maps. That's the way that you program in sequence when you're using a functional effects system. And that is not pleasant, per se. Even a for comprehension makes that better, but it's still not great. It's easier to program in the old statement way. It's a little bit of work. But that is something you can master if you work at it. And if you are willing to take that time mastering it, then you will become insanely productive when it comes time to solving hard, messy problems like some of the ones we took a tour of tonight. So if you want to learn more, I recommend checking out this repository, which has about, I think, 10 different exercises in it. And they start simply, and you can probably solve all of them on your own just by looking up Scala doc and watching a few talks and so on. And basically in afternoon, you can be to the end of these exercises, and at that point, you're going to have a good idea of how to take a library like Zeo and bring it back into your own application and start using it to solve problems that your company has. There's also some other ways you might want to hop on over to the website, which contains an extensive amount of documentation. Not complete, but it's growing. Lots of code samples. It contains Scala doc for all the versions of all the libraries. It has links to example Zeo projects. So a lot of open source, like skeleton toy apps have been made using Zeo, and also some real world applications like Netflix just open sourced a big application based on Zeo. And there's several other open source Rudder and so forth, which are built using Zeo. And then there's a growing ecosystem of Zeo libraries. I think there's probably dozens of libraries right now that are Zeo native, and there's more in development all the time. The Zeo Discord is a hopping place to be. I can't even catch up to all the chatter on there. Like 500 people, so if you have any questions, hop onto there, and I'm sure someone will give you a hand with something. And then also I have a Patreon, so if you want to get training from me and you want to support my open source work, please check that out. You can get free trainings and one-on-one chat, mentorship, all that good stuff. So that's all I have for you. I hope you've enjoyed this tour of all the cool things you can do. Well, not all, but some of the cool things you can do with a functional effect system. I've really enjoyed being here and speaking here, and I want to thank the organizers of this event for putting this on and not canceling my talk. That is awesome. And on a high note this year. Appreciate that. So any questions before we wrap up? We've got a mic in the back. What's with the Z's? Z is a cool letter. It has a lot of symmetry. No, it actually comes from, it kind of comes from Scala Z. That's the origin of this project with the Scala Z8 IO type. But then after that, we started thinking, hey, Z can stand for zero dependency because Zeo has no dependencies. It's standalone, runs on a Scala 2.11, 2.12, 2.13, and Dotty. It compiles natively across all of those. Scala.js, and almost Scala native. If we can do a little bit more work, we'll have a Scala native version running as well.
How would you compare design to Mass Effect? You saw something similar.
Yeah, so question is, how do you compare Zeo to Cat's Effect? And the answer is, Cat's Effect is actually a bundle of two different things. So Cat's Effect bundles a set of type classes to describe effect systems together with a reference type called Cat's IO. And so Zeo doesn't have any analog of the Cat's Effect type classes. And in fact, Zeo has instances for the Cat's Effect type classes, which means that if you use a library like Doobie or FS2 or HTTP4S or something like that from the Cat's Effect ecosystem, you can actually use it with Zeo no problem, because Zeo has an implementation of those instances. As for comparing Zeo to Cat's IO, I would say that Zeo is really a production grade version of Cat's IO that's much further along in terms of practical features that you need, as well as sort of heavy duty industrial strength things. I'll give you several examples. So Zeo has a notion of where effects should be running at all times, and it rigorously enforces that. If you lock an effect to an execution context, it will run there no matter what. And it will run there in a compositional fashion, such that if that effect was composed of a bunch of effects and a little tiny piece down here needed to run in this other Kafka thread pool, then Zeo knows about that and it keeps on jumping around to the right thread pool at all times, jumping back when it's done. And Cat's IO, they tried to go into that direction, but they didn't push it far enough. And as a result, if you try to lock an effect onto a position right now or some execution context, it will run on there for a while until it hits the first async boundary, and then it pops off back to the default thread pool. And it's not even possible to know whether or not in some big effect there's a composed async boundary, which means you can't locally reason about where a Cat's IO effect is running. It's just not possible. That's one of many examples where I think Zeo has a more industrial grade solution to that. Another is interruption. So interruption is very powerful. It's very amazing to be able to cancel any part of your program at any time. But there's places where you need the ability to specify this should not be interrupted but I want to open up holes in here and allow interruption in these key places. And Zeo can do that, and cancellation cannot do that. It's proposed for Cat's effect 3, but Zeo already gives you a better version of that today. And then Zeo has features like execution contexts, which are stack traces that work across async boundaries, which none of the other effect systems or even Scala's future have. And Zeo can give you fiber dumps, which is the fiber-based analog of a thread dump. So if you ever want to see all the fibers running in your system and what their state is and what they're blocked on, this fiber is waiting on this other fiber and so forth, and what's the execution trace of all those, Zeo is the only one to give you that. And then Zeo has typed error channels, whereas cancellation, it has a monomorphic error channel that locks the error type to be throwable, which means when you handle errors, the type of the effect doesn't change. So you have no information on, you're not able to use the Scala compiler to track errors statically. And you don't have a reader effect. With cancellation, you have to bake that in using Kleisli, which adds runtime overhead and doesn't infer well and all the other drawbacks associated with that approach. So I'd say cancellation is quite, if cancellation meets your needs and you're already using it, there's no reason to switch. But I think that the momentum around Zeo is founded very firmly in sort of design choices made by the product, as well as how much it pays attention to practical needs that people have, like debugging this type of async code can be quite difficult. And Zeo has a lot of things in there to help you debug it and to help you test it, to help you deploy these things in production.
Two things. First of all, is there a way in Zeo to force an async boundary?
Yes. It's called yield. Yield now, I think.
Okay. Second question. Do you have anything for distributed processing?
Yes. So it's coming along. We have ZeoKeeper in the works, which is our pure... I know. Terrible name. Some of you know where it comes from, though. It's a purely functional version of Zookeeper, basically. That is, it's nearing public release. Public release won't have everything in it, but it'll be a good start. And that's the foundation for what will hopefully become a viable, purely functional, strongly typed, resilient alternative to Akka clustered.
Thank you.
I see you're waiting on that, right? A lot of people want that. Me too. Anything else? Yeah.
So I remember your article about MTL and monad transformers and the problem about additional allocations and stuff. Did it solve this?
Yeah, so the problem here, for those of you who haven't used monad transformers, is this is not the main problem with monad transformers, but there's actually two families of problems. One is performance. So monad transformers, what they do is they say, well, you should start with a monomorphic effect type and then layer on additional capabilities. If you wanted to do that right, you would start with an infallible, an unfallible, unexceptional effect type, and then you would layer on errors, and then you would layer on environment, and then you would layer on other stuff that you need. But there are problems with that. Number one is a performance, because every additional layer adds not just wrapping, it adds the additional overhead of allocation and so forth. That's actually not the main cause of overhead, but it adds additional method calls, lots of additional megamorphic method calls through interfaces like monad error and so forth. So when you end up interacting with the data type, you're going through multiple layers of megamorphic method calls on an interface like monad error. And every layer of the monad stack means, additional layer of megamorphic method calls. And then you do have additional allocation. In some cases, you can't eliminate it. For example, even if you can eliminate the cost of an either T monad transformer itself, you're still going to have allocation on every bind when you wrap results inside the either. That can't be eliminated even theoretically. So there's types of overhead that simply cannot be eliminated with the monad transformer, and most types of overhead are not eliminated in practice. Monad transformers can be expected to add roughly 4 times performance overhead per layer of the monad transformer stack. Stack of 10, 40 times slower, at least, more likely much slower than 40 times, could be hundreds of times slower. So there is the performance drawbacks, but then beyond performance drawbacks with monad transformers, you have the ergonomic drawbacks. Because monad transformers, if you're using them directly, the way they're implemented in Scala currently, feature very, very poor type inference. So you have to annotate types quite a lot. And then if you use tagless final to help deal with some of that and isolate you from having to know everything about the monad transformer stack, that helps somewhat with type inference, but you've still got type inference problems. And then you have other types of problems. And then finally, monad transformers, I'd say, have some pedagogical issues in the sense that it's not easy to ramp up a team or ramp up people to a team that's already using monad transformers. What Zeo does is it says the most common effects that every application needs are success. You need to be able to compute a value successfully, which the other effect types have. Fail with some type value, which the other effect types don't have. Zeo is the only one to have that. And then you need to be able to access information from an environment. That's the reader effect. And those three effects turn out to be sufficient to implement lots of other effects that people use monad transformers for, including like state T monad transformer and writer T monad transformer. And so all those, logging, all of those effects can be done in terms of the other one. So Zeo's approach is you just need three: success, error, and reader, and you don't need anything else. No hierarchy. And Zeo is extremely, because these are baked into the Zeo data type, it can be super efficient in how it gives you these capabilities and doesn't actually allocate any more information. As you're flat mapping on chains of either effects, the additional error and reader type parameter add no overhead. So you really do get cost-free functionality, monad transformer-like functionality out of Zeo without actually having to pay for the cost of monad transformers in terms of performance, type inference, and teachability.
I had a question about the Zeo and basically the whole fibers construct. How transparent would you say it is in terms of monitoring, simple JVM profiling? Like how much information does it give, or how much it doesn't?
Yeah. Good question. So the story has been historically terrible, not just for Zeo, but like future debugging future-based systems comes down to using printline a bunch, because futures aren't threads, which is good and bad, but a future can be garbage collected out from you at any point in time. A future can be blocked on another future, and you can't see that in a debugger. So there's almost zero diagnostic capabilities baked into future. You have nothing but the error channel, and even that's not helpful because the stack traces you get out of future are useless. So Zeo is trying to tackle these problems one at a time. So first we introduced execution traces, which gives you detailed line-by-line information on the chain of operations that led to the failure, as well as information on what would have happened if the failure did not happen. And we also have a lossless error channel called cause that can capture all information about a failure, even when multiple failures are involved. So for example, if you go down into a bit of code and that has a problem, and then the finalizer attached to that has a problem, and the finalizer attached to that has a problem, then now you're looking at 3 different errors here. And Zeo doesn't lose any of those errors. It holds onto them all and bundles them in that cause structure. And then recently, Zeo got the ability to do fiber dumps, which give you information on all the running fibers in your system, and they can tell you which fibers are blocking on which other fibers. Now, that said, the tooling doesn't support that. So even though you have the raw sort of, fiber dump capability and so forth, the tooling that you're going to be using to debug these things is going to show you threads. And threads don't correspond to fibers. You could have 1 million fibers in your system, but only, hopefully only a few dozen threads. And that's not going to be reflected. But at least now there's a way to get access to those threads, so you can set your breakpoints on things, you can inspect them, and so forth. So we're getting closer to a point where I would say debugging becomes reasonable. But the flip side is that with fiber-based systems, you get higher concurrency and non-blocking. You get all these great properties out. It's just they've been a real pain to actually deploy in production. The next step for us is to plug this into. We're working on something called ZMX, which is basically a set of management extensions that allow you to automatically see the health of your Zeo applications, how many fibers there are, when they were started, which ones have been around too long, which ones have died. Metrics allow them, allow your application to export metrics on various things, and that's going to give you enhanced ability to monitor your application using these tools. Good question. Anything else?
If I may be wrong here, but I think the official stance is no macros, right? I completely understand, especially in the current transitionary stage of Scala. But if these are programs, would there in future be an optimizing compiler that wouldn't just interpret but actually compile these programs to achieve at least like a glimpse of what an optimizing Haskell compiler could do with flat maps? Right?
Yeah, good question. I think the answer is that, well, first off, we have a project now called Zeo Macros that people built specifically so that they could throw in cool stuff that you can only do with macros right now. However, I think that longer term, as we transition to Scala 3, it opens up the door to do new types of metaprogramming, staged metaprogramming, that we've not been able to do historically. I would expect some good work to come out of a Scala 3 native version. And also, I think that it is quite likely for comprehensions will have a successor at some point in the future. And that successor could have enhanced ability to do fusion of certain types of operations according to lawful properties. Anything else?
What are the biggest drawbacks or hurdles or inconsistencies in Zeo right now that are probably derived or caused by the ecosystem, by Scala, on which Zeo has to run on? What are the most? I wish I could not have it in Zeo, but it's Scala, so we have to live with it. Just if you can think of something.
Yeah, good question. So I'd say one of the things that is very awkward right now is composition of errors. So when you compose two effects, you have to compose their errors. And right now that works via subtype composition, or more precisely supertype composition. So you compose an error E1 with an error E2, and you get back an effect that has the common supertype of E1 and E2. And that loses information. It throws information away. And you can keep that information, for example, by left mapping, or mapping this one to be the left side of an either, mapping this one to be the right side of an either, and then composing that together, and now you have both of your errors. But that's not ideal. It doesn't have good ergonomics. So I would say that Scala 3's support for union types are going to allow us to switch from using supertype composition to using union type composition. We have two effects, we compose them together, and we get back something that can fail with E1 or E2. And that's going to make a big difference in our ability to hold onto as much information as we possibly can at compile time. And then another major pain point is the way that environments work in Zeo. You're encouraged to use subtyping for that. It's a very object-oriented thing to do because we're using intersection types. So if you have an effect that requires an A and an effect that requires a B, then when you compose those two effects together, you get an effect that requires an A with B. That's the intersection of A and B. And that works out okay. However, Scala has no ability to easily construct proxies. And it turns out when you do this sort of intersection type composition, you end up building structures that are basically proxies to other structures. And Kotlin, for example, makes construction of proxies very easy. It has a whole keyword to do that. Scala doesn't have anything like that. Again, I think Scala 3, it has export keyword, it has trait parameters, it has some good stuff in there that's going to make some of that easier, but it's a very noticeable pain point in day-to-day programming with Zeo. And then the other thing I'd say is it's tricky to implement some of the low-level stuff in the interpreter without allocations and whatnot. Some stronger performance guarantees with Scala would be nice. Having it do the smart thing would be ideal. There's actually some bytecode instructions that are very hard to make it generate, super hard. And of course, the inliner basically doesn't work, in practically speaking, in 2x. I mean, you can make it work through contortions, but basically it doesn't work. And then the the other pain point revolves around how difficult it is to acquire information on where closures were created. And that has implications for how Zeo does execution tracing. It does execution tracing by looking at the class of the associated lambda and parsing it into memory, decoding the bytecode, extracting out various bits of debug information, and then caching all that to make it really fast, which works, but it's not ideal. And ideally, Scala would have a mechanism. Right now, you could potentially do it through macros, but again, Zeo is no macro because it has to cross-compile in Scala 3. That would allow you to say, I want the line in which this is defined, the line and the source and the method, all that stuff in which this thing is defined, this thing that was created was defined. And having that would also be a game changer. And as far as I know, that's one of the things that's not going to improve in Scala 3. Good question. All right. Well, thank you all for attending my talk. It's been a pleasure.